here's the kind of outline that we have for today. I'll be starting with basic searching algorithms, linear search, and then I'll be doing some benchmarking with different programming languages, and then I'll get to tree-based data structures into some more advanced searches, so such as binary search trees. And then the main topic of this talk will be B-trees, which is a more advanced data structure that's very, very useful, both in the context of Progress OpenEdge and outside of it. And by the way, this is kind of a linear plan, so I assume that whenever I go through some topic, I assume that you've understood it, but if you did not, please raise hands. Do not wait for the end of the session to ask your questions, and I'll be happy to answer any questions you have at any time, okay? So I'll start with a kind of simple problem. Let's say we're given an integer array with n numbers, and we wish to query wherever and a specific number is inside the array. So that would be a little bit, a practical example of that would be if you're searching for, let's say, a customer ID, whether a specific customer exists and you wish to pull it out of the database. Okay? So the kind of naive solution would be to simply take a for loop and go through the whole array and search whether a specific number exists in it. A visual example of that would be simply you go iteratively through the array and you search whether a specific index exists. So all in all, at most you will be doing n iterations like this, because in the worst case scenario, you'll have to go through the whole array. Now, just for fun, what I did was do a little performance benchmark where I looked at some different programming languages and saw how, with different inputs, how quickly they run. And as you can see, as in most cases, C++ is by far the quickest language. But near it, we have Python, which is a little bit surprising because you might hear from different contexts that Python is really slow, and in most cases it is. But for this specific scenario, where we have just a simple script, let's say to run, to search for a specific element in an array, it's quite quick because Python is often used. Well, that is the reason why Python is often used in data science, since it can do these operations very quickly. And but nevertheless, C++ and Python are quite far apart from each other, because if you see, well, it's kind of hard to see, but so I'll just tell you, C++ and Python are about 2 times slower, or C++ is 2 times faster than Python. It's just that in the graph, since it's a logarithmic graph, the difference is not that noticeable. Now, near these programming languages, you have JavaScript, which is quite a bit faster than Java, which that's another key note to take. That means that sometimes running code in the front end, if it's just a simple operation, might be quicker than actually going to the back end and running it there. This is just from the perspective of raw performance, so not about security or anything else, because sometimes you might not want to run JavaScript since it's easy to manipulate. Just from the perspective of performance, JavaScript is quite quick. Now, what might interest us the most with Progress OpenEdge, which for quite small inputs, so between 10,000 and 100,000, it runs quite fast, or at least in the worst case scenarios in the middle of the pack. But after between around like 50,000, it gets quite slow, and this is mostly due to the limitations imposed by Progress OpenEdge. For instance, you cannot use an array outside of a specific range, thus you have to create a temp table or some other more complex dynamic structure, which does lead to a drop-off in performance. But this is not a knock on Progress, since the other programming languages, they're mostly general, while Progress is more geared towards a specific use case. So most of the time, or in every single case, you shouldn't run a for loop on an array, but you would use indexes or something else, some other Progress key feature to heighten performance. But that's just a kind of quantitative way to tell you why you should do Progress the way you should. Now, an improved solution is that we should notice that usually data is presented in an orderly way. So we do not have just any random array, but for instance, the array could be sorted. And in most real-world scenarios, the data that we use is indeed sorted in some orderly manner. In that case, if the array is indeed sorted, we could use a binary search, which is a very famous kind of key algorithm, one of the first algorithms that you would learn in a data structures and algorithms course at university, for instance. And how binary search works is that if we have an array, we take the middle of it, we take the middle element. Since the array is sorted, everything to the left is smaller than the middle element, than the pivot, and everything to the right is bigger. So here's a nice visualization of how that works, but this algorithm is kind of intuitive because we use it all the time without even thinking about it. For instance, whenever we search for a specific word, whether it exists in the dictionary, what we do, since we know that in the dictionary words are sorted, right, A, B, C, D, then we first take the middle of the dictionary, and then if we can't find the word, we know whether it's to the left or to the right. And that way we don't have to flip through all the pages, but we can skip a lot of the pages all the time. So this works out very quickly, since you're skipping basically half of the array on every iteration, so it works basically light speed. In short, there's no need for a benchmark, since in every single programming language it would run almost instantly, even if the data is very large. Now, that's nice. We've kind of found an optimal solution. However, in the real world, a static array is not enough, since if we have a system, we will not have a constant user base, but we'll have users coming in and out. So we wish to add and remove elements. In this case, there are a bunch of different solutions based on the case that we have. One of those solutions that are used quite extensively are binary search trees. And here I gave a kind of short refresher on the terminology used in data structures and more specifically in trees. So you can see at the top, we have the root, and then we have edges connecting. So connecting the nodes, and then everything connected by the edges. So we have the parent up top and the child down at the bottom, and then basically all the other terms that we use. And as you may notice quite clearly, that structure is specific in the way that we have put together the tree. So binary search trees are used because everything to the right is bigger and everything to the left is smaller. Just like in binary search, that's why it's called a binary search tree. So it makes sense so far what's a binary search tree? All right. So we have binary search trees that are used extensively, very useful. However, in some cases, we need to go even further. And then we have B trees, which are sort of, I call it an extension of binary search trees, since just from this image, you can already see that they're a bit different, but almost the same, right? There's just something else added to it. Now, before going to what B trees are more specifically, I should probably talk about use cases, why B trees are used. And the first key use of B trees is in the APFS, which is the file system used by Apple. So this little company, they use it quite extensively in both macOS and iOS. And basically, if you've ever flipped through an iPhone or searched for a file in a Mac, you've used a B tree. Now that's nice, but in our case, what's more important is that B trees are the key data structure, basically the building block of database indexing. And here's a quote from the documentation of Progress. And Progress tells us that every single index in an OpenEdge database is a structured B tree. So whenever you add an index to a table or to a field or to whatever, you're adding a B tree. Now that I've told you why B trees are quite useful, the key question to ask is why are they used so much? And the answer would be memory. Now, a little bit, a precursor kind of to everything would be how is computer memory arranged? And I've given this sort of pyramid kind of schema, where at the top you have the fastest memory, which is CPU, registers, cache, and they work very quickly, but they're also very expensive to make. Now, in the use cases that I showed you, we have file systems and databases, and in databases, there was already a talk yesterday where someone migrated a huge database with 10 terabytes of data. In that case, you would only use main memory and external memory, since that's really the only way to actually move that much data around. So B trees work very well with main memory and external memory, and it's because of how computer hard drives are conceived. So you have right there a whole, maybe I could use a highlighter like this, or a pen, I guess, a laser pointer, yeah, right. So you have this arm right here, and at the top of the arm, we have a read-write head. And how it works is that you have this read-write head, which stays stationary while the disk spins around. And when it's stationary, it can read sequentially, basically like this, all the data very quickly. But the key is that if you have some data right here and then some other data right here, it's quite far away, and then the arm has to move in order for the read-write head to actually be in a different place, because it couldn't read it in a sequential manner. Essentially, the bottleneck is this exact read-write head movement, since even though computer hard drives and SSDs and everything we have at the moment, the marvels of engineering, nonetheless, this read-write head movement does take some milliseconds, and in a database with terabytes of data, it has to move so many times that the milliseconds add up, and that's the bottleneck. Thus, B trees are conceived in such a way that the read-write head doesn't have to move that much, because the data is read in a sequential manner. Okay? So far it does make sense why B trees are used? Okay, very nice. Then we can get into the properties of B trees, and here you may see two different B trees, and I'll briefly go over the actual definition of what a B tree is. So every single node in a B tree has some specific properties. For instance, it has some number of keys, and all the keys are sorted. So for instance, in the tree up top, you could see that everything is sorted. So we have 50, then on the right we have 60, 70, 80, and everything's sorted. We also have a Boolean value, which tells whether a specific node is a leaf or an internal node. So the nodes that I have outlined here, they're leaf nodes, and the nodes that are not outlined, they're internal nodes. Furthermore, each internal node has a list of children, and the size of the list of children depends on the length, on how many children the parent has, okay? So for instance, since we have right here, we have 10. Since 10 has 2 children, since 10 has only one key, it has 2 children, right? Then right here, since this specific node has 3 keys, it has 4 children. So it's basically the number of keys plus 1. That's what I wish to explain. So then the children are put in such a way that they satisfy these three inequalities. That's just a kind of formal way to write it. But for instance, in this specific case, we have 12. So everything to the left of 12, that's just smaller than 12. Then this specific edge leads to everything that's between 12 and 5. This leads to everything that's between 15 and 18. So we have 16. And then this one leads to everything that's larger than 18. So this specific structure allows us to search very quickly. Next up, another invariant that we keep is that all the leaves should have the same depth, must have the same depth. Thus, as you can see, the tree is kind of flat in the sense that you could not have any more nodes at the bottom, because all the leaves must be on the same level, right? Furthermore, we have a specific integer, which is called the minimum degree, which tells us how many keys a specific node has. So it's between t minus 1 to 2t minus 1 keys. So for instance, in these cases, t, the minimum degree, is equal to 2. So every single node has between 1 and 3 keys. A node could not have 0 keys, and a node could not have 4 keys. That's just a way to keep the structure, the structured environment in the B tree. And if the minimum degree was, for instance, 3, then it would be between 2 and 5 keys. Right, so phi does make sense. Yes, very nice. Then this specific way of building a B tree allows us to search quite quickly. And here I have presented the pseudocode, how we may find a specific key, whether it exists in the B tree, but it might be nicer to actually just show you it practically. And I have a visualization right here. So if we create a specific B tree like this, how the search works is that we look, let's say we wish to find whether 12 exists in the B tree. Then we start from the root up top. And then we check for the first element, which is bigger than 12. We find it. And then we go down this specific child, since we know that in this specific subtree, everything is between 10 and 17. So if 12 exists in the tree, then we'll find it right there. And then we recursively do the same process. So we go to either to the left or to the right. Since we know we're looking for 12, which is smaller than 13, then we go to the left. And we do the same process again until we find that 12 exists. All right. So search is quite simple and works quite well, quite quick. But what if we wanted to insert, which was the key problem, since with more basic structures we could not insert data. And the idea is that we start from the root, we traverse the tree, and since we already know how to search for a specific node, what we'll do is we'll run the search, find where it should be, and put it right there. Now, that works fine in most cases, but since I already said to you, and I might actually go back into the visualization, let's say we wanted to insert the node right here. So if we have something, let's say 300, what happens is that when we reach the specific node where we should put 300, it's already full, since you cannot have more than 3 keys. So we must do something about that. And the idea is that so formally, a node is considered full if it has 2t minus 1 keys. In the previous case, we had t is equal to 2, so if it had 3 keys, it was full. Thus, the idea is that we split it at the median. The median is just basically the middle. And we split it into 2 specific nodes, like that. So as you may observe, the median is 6. And we put 6 up at the top, so up into the parent, and then we split it into 2 different nodes. That way we have 2 nodes that are not full. Now, since we're going recursively, it might be the case that the parent node is full as well. And in this case, we have to recursively do this process. And the idea behind it is that we will always fix the nodes first and only then insert. And a kind of analogy would be if we have a very messy cupboard or a drawer, we have 2 ideas how to put an item inside this drawer. We could either put it in and continue the mess, or what we could do is we could place half the items in a different drawer, and then we have 2 different drawers that are not messy. And that's what we will do. Whenever we find a node that's full, we will make sure to split it into 2 nodes that are not full. So here's how the algorithm works. So we start at the root, as always, and then if the root itself is full, then we split it, and then we traverse the tree, and whenever we find the node that's full, we split it as well, and adjust everything accordingly. And then we insert the key into the leaf. All right, so I'll head back into the visualization. So if we have this specific, the simplest case is when we have a tree like this. It looks like an array, but it's actually a tree. And if we insert something in it, let's say 6, then it finds that the specific node is full, and it splits into 2 like that, and then it places 6. Now, to present the recursive way, it could be that we wish to insert something in here, let's say 20. Oh, that's the wrong button. All right. Just a sec. I'll reset everything, and then we have insert. And then we find that this specific root is full. Thus, what we do is simply split it like that. And as you can see, the tree size got bigger. So the tree height was 2. Now it's 3. And then we just place 20 where it should be. Now, to showcase the split child method, because a child could be full as well, not just the root. If we wish to put 30 in this tree, what happens is we go down to this specific child, and then we find that it's full as well. So we split it, as we have split the root like that. And then we just place 30 where it should be. So far it makes sense? All right, very nice.
Question.
Yes?
If our maximum node width is 2t minus 1, then why did that node have?
So in this specific case, the degree is 3, right? So 2t minus 1 is 2 times 3 minus 1. That's why the max width is 5.
So what is t?
I thought that the maximum was 3, but now on the bottom right you have 4.
So the maximum, it depends on the specific degree that we set at the start. If we set it as 2, then the max is...
Degrees height. Degree is the height, okay.
Yeah.
Okay, because I thought earlier in the session you said we always use 2.
No. I did not say that.
I misunderstood.
That's fine, totally fine, yeah. So after insertion, we have deletion, which is kind of the antithesis of insertion. And the idea is pretty much the same. We search for the specific node, and then we delete it. But we have the exact opposite problem, that a node could be too small. Formally, that means that if it has two minus 1 keys, then it's too small. And then we have to do something about it. And the strategy that we'll utilize is pretty much the same as fix then insert. In this case, it's fix then delete. Every time we find a node that's too small, we'll fix it. More formally, we should observe that whenever a specific node has more than t keys, then we can delete one key from it, since every single node must have at least t minus 1 keys. And in this way, we ensure that we can always delete at least one key from a specific node. And the deletion algorithm has a bunch of different cases. So if we reach a leaf node, then we can just delete it safely, since we've used this method that allows to always delete at least one key from the node. But if we find some kind of node which is not a leaf, it's internally, and it has the key, then we have to do something about it so that we could delete from it. And I've written out the steps formally, but I suppose that it should be simpler if I just show you. So we have an example like this. And in this case, degree is 2. So we can have between 1 and 3 keys inside a node. And if I wish to delete 25, which is right here, then what I do is, just a sec, I will reset it. So if I wish to delete 25, then I reach 25, I find it here, but I cannot delete from it, since if I do, then this specific node will have only one key, but it will have 3 children, and it should have one more children. Well, basically the invariant that we should hold is that if this specific node has two keys, then it should have 3 children. If it has one key, then it should have 2 children. Thus, I have to do something about it. Therefore, what I do is I take the biggest node that's smaller than this one, and then I basically delete it from here, and I place it inside here. That way, the specific structure is kept tidy. Likewise, if I wanted to delete 31, I would take the smallest element bigger than 31 and swap it in this specific way. Okay, so that's why 30 went to, instead of 31, we now have 30. All right, and there's another case. For instance, if we wish to delete 18 here, we cannot take from the children, since if we try to take 14 here, or 21 or anything else, we'd remove one node, and we do not wish to remove any nodes. Thus, we just merge them together like that, and then we delete 18. All right, so that should be clear so far, is it?
If I
Yes?
look at a node as an object,
Yes. Oh,
what are the attributes of a node object? So one is the node of the smaller ones, but I see they have 3 children.
yes.
So describe to me the 3 children. One is the smaller ones, one is the bigger ones.
Yeah.
What's the middle one?
So the middle one, I'll just show. Do you have any cases right here?
You see here 82 and 95
Yes.
have 3 children.
Yeah.
So
So
is 82 and 95 one node object?
yes, exactly. You would
Yeah?
implement it with, let's say, an array. That would be one way to implement it, have an array.
So then the 71, 33, 76 is a child object. The maximum that object can have is 3.
Yes,
3 children.
exactly.
And then give a conceptual description of each of these 3 children. So the left one is the smaller ones,
Yes.
smaller than the smallest one.
They,
The right is bigger than the biggest one. And
Yep.
what's the middle?
the middle is everything between, yeah,
Okay.
between 82 and 95.
Okay, got it, yeah.
All right, nice. So I can go further, and there's another case when we've reached a specific node without the key. And in that case, what we do is there's this notion of borrowing. So in this case, for instance, we're looking for 84. And as you can see, 84 has only one key. And we could not delete it. Thus, what we might do, and this is a sort of more advanced movement, to make sure that the node which contains 84 is not too small, we borrow from the sibling of it. So it might be clear from this picture. What we do is just
You flip them.
exactly, yeah, you flip them. And in this case, then if you do borrow from it, then you add one more key to it, then it's not too small, and then you can safely delete from it if you need. And then there's also another case where both siblings could have only two t-1 keys, then you just merge them, as you did in the second case. And I'll go back into the visual. If you have a case like this, which is actually the same one that I showed you in the slides, and you wish to delete, say, 88, and it goes to the specific node, and it performs the borrowing. So it borrows from the left. And essentially, it does the same things recursively. So whenever you reach a node, you do one of the, you activate one of the cases. Thus, in this case, you borrow once again, since you're going down to this, to the right node, right? The one that has 93. So you borrow again to make sure that the node that had 93 has one more key. And then you go down to it, and then when you find 88, you can safely delete it. Okay, so in this case, you had to borrow 2 times in order to actually get to 88 without making any nodes too small, without deleting any nodes. Makes sense so far, or should I go to more? Yes?
For the old timers,
Okay.
how I look at it is from, in our data structure, it used to call linked list, right?
Yep.
We used to do this with linked list. Now all they've done is created an object out of a linked list. You have to start viewing it from that perspective.
Yeah, so you could actually look at it through this lens where you have a linked list and then pointers leading to the children, and the children themselves are linked lists as well.
So it just becomes an object with pointers at the end.
Right, but we were doing a bunch of borrowing and stuff before we ever got to 88.
Yes?
Why was all that housekeeping necessary before we even knew which child node to delete?
So I'll reset. What happens here is that we don't know exactly where 88 is, but we know that it's in this specific subtree right here. And you see that we might have to delete something right here. So the strategy works in such a way that whenever you find a specific node that's too small, you fix it, because you don't know whether you'll have to or you'll not have to delete from it. So it's just kind of for safety. That's why it's done this way.
So why does it start out too small?
Well, it started out.
It shouldn't be starting out small if your algorithm is correct when it's building it in the first place.
It's well, the thing that we're looking for, it's not that it's too small, but it should have one more, at least one more than the minimum. So in this case, the node would be too small if it has 0 elements. right?
Right.
And what we want to do better than 0. We want to have at least 1.
Right.
In that way, we could delete from it safely.
Right.
So since 1 is the minimum, then we wish for every single node that we traverse to have at least 2. That's why we borrow, to make sure that we have 2 keys.
My daughter studies computer science, and I've seen her work on this problem.
Yes, it's like,
And you know how she solved it?
yeah.
ChatGPT.
Yeah, actually, ChatGPT is quite good at these kind of algorithms since the classical.
Given the problem, it perfectly does it.
Yeah. So this specific case does make sense?
Mm-hmm.
Nice. So I may go further and all the cases, we hold different cases. And here's a nice slide of what we did. We implemented the specific data structure, the B tree, in different programming languages. So is there anyone who knows all of these programming languages?
One of them is Python, right?
Top right is Python, right?
It is, yeah,
And to the left, that's C++, no?
exactly. Oh, no. To the left is not C++ because we,
Oh, sorry. Yeah, yeah.
Bottom right is.
yeah, C++ is bottom right. And then we also have ABL right there, all nice and shiny.
Oh my goodness. Yeah.
And what I've done is, just like I did at the start, I benchmarked everything. Thus, we can see clear numbers of how quickly these data structures work. And as usual, C++ is the quickest, and Java and JavaScript are kind of in a race. You can see sometimes JavaScript is faster, sometimes Java.
How big of a B tree?
So right here, you can see 10 to the 6th. That's a million. So we have a million,
Okay, so
a million
it goes
keys.
from 1 to a million.
Exactly. And C++, for instance, runs under a second, while JavaScript running around a second and a half. And then Python is much slower. It takes almost a minute. So what C++ does in under a second, for Python.
Is that to build it, or to
In this specific case, we had a mix of building, and then we had a insertion, deletion, all the operations.
okay?
So
You run the same sample space against it.
So build is build a million, up to a million then.
yeah, in this case, we had right here, n is almost a million. I remember that this specific case was n operations, so you can essentially imagine it, let's say, add 300,000 elements, delete 100,000 elements, and add 100,000 more elements. So it's a mix of all. Basically just a bunch of different operations.
But progress is not on there.
Yeah, progress is not on there because it would be very sad. Progress did work quite well. Well, the progress implementation, the one I wrote, was very slow. So I asked one of our senior wizards to make up a better implementation, and it ran quite fine. It was around Python up until, let's say, right here. It was basically catching up to Python. And everything bigger than that, it basically did not run. Well, it could run, but maybe we'd have to test it for an hour or so.
A million objects, well, however many nodes, that's how many objects you get, right?
Exactly. So, however, there's a specific lead that we could try that I was notified of. We could insert the B tree into the DLL file, and then it would run much faster, but we still couldn't implement it quickly enough for the conference, but that might be possible. We'll see, maybe for Valencia, right there we could show where Progress could actually run quite quick. But we'll see if it will be possible. Anyway, any more questions from this specific benchmarking? Then I may go into a couple conclusions that we may draw from this. So these search algorithms, a lot of them have been developed in the 90s or maybe even in the 80s. So they're classical, that's why ChatGPT is so good at them. But they are still the foundation of everything, basically. So there's no need to try and reinvent the wheel and create something new when what we have at the moment, it's almost optimal and it runs so quickly. Thus, as I wrote here, proven tools, timeless logic, that is essentially the context of B-trees. They remain the data structure used, as you can see, both Apple and Progress and pretty much anyone, any single database still uses B-trees, even if they have modified them, but the backbone, the main foundation still remains the B-tree. This specific kind of structure still remains as the main point of how database indexing works, right? And any more questions? No? Then if you have anything more about B-trees or about anything else, or about Baltic Amadeus as well, you may Google me, or not Google me, Gmail me, or write an email to me right there. Okay, thank you.